So one way where we disable those things, the another way is here. So when we do the simulation in the software, it goes like this: simulation. Next, we define material properties. We apply loads. We apply boundary conditions. We mesh the design. We do the analysis. It is simple, straightforward. Nothing to miss out. Nothing to miss out. Okay, thanks. So here, finally we see the results, different types of results that we have got. Okay, so we'll pull this. Okay, so for the case of pressure sensor, piezoresistive type, I was talking about Wheatstone network, right? So if it is a top view of the structure, just like this, we have resistors that we keep like this. So how is our Wheatstone network? Just like this. Right? So at some point we, this is our output, P out. Somewhere we cut it here. We call this as V in. Correct? Okay. So now this is the condition here. So what we say is R1, R3, R2, R4. So there is a difference connecting it like this. Correct? So here there is a difference between the two, right? So what we do here is the top view. What you are seeing is the top view. Okay? So top view. So when these piezoresistors are mounted here, I'm saying it is not kept here, it is mounted. Meaning, if you take the cross section of it, the piezoresistors are not above this. Okay, piezoresistors are embedded. Okay, so these piezoresistors are embedded using ion implant. Okay, using ion implant at 4 locations. We do. So we have resistors, we have a wire. Okay, so what we do, we connect it like this. It goes like this. Okay, so it gets connected this way.
This is top view of the circuit.
This is the top view. Okay, if you look at the cross section view,
Means now I have to use the piezoelectric material. So the switch is there.
no, piezoresistive material.
Okay.
Yeah. So here what happens, we have the cross sectional view like this. So in the cross sectional view, we have these, if I cut it like this, in the center, for me it appears only this much, correct? Correct. In the center, if I cut it, only 2 is appearing, right? So this back edge is there. Okay? It is a back edge. So again, in this we have 2 types. Fixed type, differential. So even in this one, though we have capacitive type, piezoresistive type, We have in this also fixed end. So now pressure is applied from bottom. So there is a small expansion that happens here, like this. Correct? Okay. Due to that small expansion, what happens here is these people who are there, 4 of them, will start experiencing upward force. So that results in developing stress like this. On the top view, if you look at, so these are stretched like this. The fellows here are stretched like this due to stress. Due to the maximum displacement is in the center. So it becomes like the cross-sectional view is like this. Okay, this is the top view, this is the cross-sectional view. Okay, so the resistors here experience stress. Okay, so these are piezo resistors, right? Piezoresistive material. So in piezoresistive material, rho L by A is the resistivity. Length. So when that length changes, area changes, so resistance will change. So for the applied pressure, there is a certain voltage drop that happens. That voltage drop is giving me, or it is sensing some pascal of pressure from me. Okay, so we'll go into detail of it tomorrow. I think I'll be starting from pressure sensor. Okay, so this is how it is. This is the fixed type. What happens in differential type? This is sealed. This is sealed from the bottom. There is a reference pressure that is already there inside. Okay? This is a gap inside. It is sealed. Okay? Then there is a reference pressure that is there inside, due to which the pressure is applied. There is a change. So we have a reference pressure. We have the pressure here that comes in. So due to the difference of it, we can build a readout integrated circuit again, which gives us, this is the pascal of pressure that's coming. So it's not fixed actually, it's called absolute. That's the technical word. Absolute and differential type of pressure sensor. So if such is the case, then we use static piezoresistive. Okay. So when we use piezoresistive, the condition is in the load, what should be the applied? So we give the phase, pressure, phase, on the phase or on the node. So here we give pressure, phase. We select, we want to apply pressure on that fellow, on that region, that phase. So we can enter some value, say 10 pascal of pressure. Click OK. Okay, and then we apply, and here is, I think I skipped material. So here material, check modify, and then click. So this material which turns red is what is selected. So here we need to apply material property of that material. If it is silicon, we have to apply. But default, we have the material database here. You can select which material you want. Okay. So we have different types of materials. So you can select. In the event you don't have a material of your choice. Okay. So then what we do is we change the values here by double click. Say 63, 69. Okay. This value 160, 160. So some 697 kind of thing. So you can change the values and then you can export matte ML. When you click on this, you can save the material what you created for future use. Okay? Because nowadays innovations are coming so fast that we cannot give materials for each and everyone who wants to use it. We have most generic materials that are there. That's how I think any software does that. So here we can do. Okay. So now simulation, material property, loads, boundary, mesh, analysis. So that's how it goes. So now for piezoresistive type of sensor which I explained, so now we saw that this is the stress component that we, so for thermal, we saw thermal electrical, how it goes. For other types, like we have magnetostriction and magnetic actuation. Due to EMF, electromagnetic force, so there is a displacement that can happen. So we can even simulate that as well. So here we will just say that yes, we will do static analysis. You should give it a thought that what should be the analysis type. Analysis type is based on the type of sensor that we are doing. Okay, so what is a type of sensor? Again, it comes, the fundamental question that comes back is, what are the input parameters, what are the output parameters, what is the physical behavior of that sensor. Okay, so that's how we decide and then we proceed it. Okay, so that's how we use this thermoelectromechanical module. Okay, so simple, which I told that this is a Lagrangian based model. So here simple has different elements. Just pull them.
Okay. Like PCB maker
Circuit designer. This is for circuit designer. Yeah, is there. So circuit based designing, and these components are for circuit, but there are MEMS elements also. So beam structure, cone structures, plate elements.
Also, how we can take our own MEMS element? For example, I have designed my element. So I can import that element in this.
No, you cannot import an element. You have to create your structure using the elements here.
Okay. Again, we have to make.
Yeah, I mean, just the elements are already available. So in case if we want to create a simple cantilever beam, we have beams. Different types of beams are there. You just pull that, keep it, double click on it, change its dimensions. That's all. Okay?
So if I want to make a different design, then
Like what?
for example, I want to make a different design.
Different meaning you give me one design.
Switch, I have made a different switch.
Okay?
Or I just want to check what will be the resistance of this particular switch.
Electrical resistance. Okay?
So how so we cannot recall our device here.
No, no. I'll tell you the purpose of using simple. Why we wanted, why we should use simple, I'll tell you. Okay. So these MEMS devices, whatever we simulate, are all FEM based tools, FEM based simulation. And we also need to remember that FEM simulations are extremely time consuming. Sometimes some structures runs 3, 4 days, 5 days simulation. Okay, so something like gyroscope, accelerometers, which are really big structures which are made of silicon, which have a lot of thickness. So for which 2, 3 days, 4 days, 5 days, sometimes it goes on. Okay, based on the PC compatibility. Okay, so here this lump modeling reduces your speed, so increases your speed by 1000 times. So here whatever you wanted to simulate using FEM model, some 10,000 number of data you wanted to generate, that 10,000 number of data in FEM, if it takes 4 days, it takes not more than 5 minutes here. Okay, so this is one advantage of using simple. Advantage of using simple is one is that it is a speed king. Okay. A. B is you can integrate outside electronics with your MEMS device. D. 3. FEM simulations are all ideal conditions, meaning your damping is zero there. Any software you take it, unless you don't define damping, damping is zero. And we also know that there is no system in the world which has damping zero. Right? And damping is decided by the environmental conditions around it. So what we use is ambient condition, ambient parameter. At what temperature you want to use it? At what pressure you want to use it? What is the viscosity of the gas that you are working at? Okay? So ambient conditions around the device is what you can set. So in case if we want to, this is a single beam. In case if we want two beams, we can set this beam in Z gap, beam in Y gap, meaning these are the elements, meaning the name itself says beam is a beam. Beam Z gap. In Z direction you have one more beam and you can define a gap size. Beam Y gap. One beam comes here, one beam comes here next to each other. Beam 2 gap. 2 gap meaning it is like this. One beam here, another beam here, another beam. You can define the number of pairs so that it becomes like this. Of course, gaps are there in between. You can define the gap as well. So that becomes your cone structures.
We can change the property of beam, sir?
Property of the beam you have to change it, because whether you are designing using silicon or quartz or what material, you know, right? So here also we can define material properties. That is very much important. Without material property we cannot just simulate. In case if we forget to apply material property, simulation will not say that you have not applied. It will take by default polysilicon. By default is polysilicon. Okay. So polysilicon properties are taken and then it does the job. Okay. So this is the simple part of it. So here we can do MEMS 3D visualization as well. And another part of using simple is, say some structures that we wanted to create in FEM 3D model may not be easily created in simple. Like the way sir mentioned of some structure which I want to do here, how to bring in that model. Okay, some standard structures like beam structures, cone structures, plate elements, those some standard ones we can bring in.
It's like, sir, in morning session they were discussing the V-shaped bridge over there.
Exactly. You mentioned of V. I wanted to give an example of a curve. Whichever. Say which is a non-standard type of design, whether it's a V type of cantilever beam or a curved based one. So when some non-conventional structure are designed, what we do is there is something called as macro model extraction. Okay, macro model extraction is a simulation in thermoelectromechanical module. So macro model extraction does three things. So macro model extraction can import rigid body variables. You can study spring constants, which is a major factor. There are expressions or equations for some standard structure to analyze spring constant. But some serpentines like a structure, okay, for those things what we generally do is we apply a unit force, see the displacement, Stokes method, F is equal to Kx, okay. For the force applied divided by displacement is our K, okay. So that's how we do and get the spring constant. Okay. So here we have macro model analysis for electromechanical reduced ordered modeling or mechanical reduced ordered modeling. If the device is not carrying any electrical signals in its body, then we use mechanical reduced ordered modeling, or else we do electromechanical reduced ordered modeling. Okay. So most of the capacitive type of sensors does go through electromechanical reduced ordered modeling. What it does, sorry?
Simple analysis can be able to see the result. Like, suppose we are giving input, can we able to see the output in the simulation? Simple analysis.
Yes, you can see it in two ways. A, 3D visualization. B is through graphs. You can get it, but 3D visualization of MEMS devices only, not your electrical signal. No, sorry, not your electrical circuit. Okay. So what happens in electromechanical reduced ordered modeling? We have to do three types of analysis: model contribution, strain energy, and mutual capacitance. What is model contribution? Model contribution is it calculates the resonant modes that are there in your device. First, we have different resonant modes. In electrical terminologies, we say it as noise. At higher modes, we get higher modes of frequency. So we have, so the amplitude, we have one primary mode, secondary mode, tertiary mode, multi-mode, right? So those amplitudes are very less. So the primary mode is what our focus is. So what we do is it captures the model contribution and then it goes to strain energy versus model amplitudes. The strain energy across the structure is captured, and finally mutual capacitance versus model amplitudes. The three files are three simulations are done, and then it generates three different types of files. Okay, so when it generates those three different types of files, I can go to simple and then use these micro model element. So this is my black box. This is my black box. I import those three files which were generated using the macro model analysis and import on this one. So this is my FEM equivalent device now. Understood? This is like an FPGA, blank FPGA. Whatever you load, it is that. Okay? So now we have embedded the code of our FEM simulation output on this one. Now I can collect all my electrical signals here, or electrical circuit there, to analyze those signals. So this is the fourth advantage of using simple. Okay? So for non-conventional structures, you can use simple by doing this macro model analysis. The advantage of using the macro model analysis or doing macro model analysis is the files that are created using the macro model analysis are the ones can be converted to Verilog file, PHDL, PSpice, Simulink, equivalent files.
Directly
Converted.
Yes.
Yes. And then you know where those files are.
So we can implement this circuit on FPGA also.
No. Not these files. The files which are created using the macro model simulations.
We can put these files into the library of Verilog or VHDL. Then we can use the different circuits using this element.
Yes. You can do. No. Not this element. See, I'll give an example. I have designed an accelerometer. I have designed an accelerometer where I I did the macro model analysis. I have captured all types of behavior of this accelerometer device, converted this to a Verilog A file. Okay. I use Open Cadence software. I import this Verilog A code and put it. It comes as a box or an element. Cadence cannot design and give you a gyroscope. And understood? Or an accelerometer, whichever. So it cannot design an accelerometer there. So this gyroscope IntelliShoot file goes and sits there. Without signal conditioning system or DAC, the purpose of your MEMS device is useless, which IntelliShoot cannot do. So design everything here.
We can import those into the cadence, and cadence you can use a CMOS or anything.
Yes.
Circuitry of
yes. So now connect all those circuitry part of it. Of course, basic circuitry signal conditioning can be done on simple.
Okay.
No problem.
Complex will be there.
Complex will be there. Some controllers and all you can bring in there. Okay, or else in case if you want to connect it like a digital IC kind of a thing, you can do it. So many advantages are also there. Okay, so there you can integrate both of them. I'm just using the word cadence because it is being used by most of the people. You can use Synopsys also. You can use Tanner, Mentor Plastics, whichever we are comfortable. So Verilog A is what I'll say. Verilog A, VHDL, Simulink, MATLAB, PSpice, HSpice. So these are the files. So all is what I'm trying to say is, as a whole system where a signal conditioning is very much essential and the MEMS is also essential, can be go hand in hand. The complete system is addressed. Okay, this is one. Again, what is the final outcome in your cadence? Mask layouts. Yeah. Okay, mask layouts. Bring those mask files back to IntelliShoot, design your process flow. Right? Okay, the major disadvantage that we have here is we cannot have one single process flow for MEMS design and IC design. We cannot have it. Though we integrate it, we will have two different process flow files. The only reason is our IC circuit layouts are all in nanometers. Our MEMS devices are in micrometers. The same process flow it will not apply. So hence, till now we are unable to bring both of them on a common platform. So even whatever the accelerometer gyroscope that we are using in our phone cars today has two sections. A wall is between them. One is MEMS, one is signal conditioning. A wire is connected between them. Both are fabricated separately. Put them with a wall in between. Pack it. Okay, that's how it goes. So as such, what I am trying to tell you is, the software has everything of MEMS, whatever you require. Okay, outside of it, as a whole system that you want to create, it is compatible there. Okay. Yeah. So here also you can convert it. You can convert this element into an equivalent VHDL also. Of course, macro model cannot be converted. Maybe you can take some electrical thing of 555 timer. So prepare a VHDL file for a 555 timer. That is possible. Okay. So okay. Okay. So this is some basic overview of the software, that these are the things. So I summarize. We started with two different types of approaches of design, top-down approach and bottom-up approach. and we saw what are the two different types of analysis for structural analysis. One is lumped Bayes modeling, one is element modeling, and one is FEM modeling. Okay, and what we also saw going further is we can simulate MEMS devices with outside electronic circuits also. Okay, this completes the whole thing. On the design part of it, the fabrication process flow we have still not touched. Okay, fabrication process flow is a simple three-step process, I will say. Deposition, lithography, etching. Okay, we will give more stress about these fabrication process flow on Thursday onwards. Okay, till then we will work on the device itself. If time permits, on Wednesday second half we will try to do it. Okay, so we will start from there. The challenges of the fabrication, what is undercut, what is overcut, what is corner compensations, those things we will see. Okay, so now we will understand what are the types of device that we will be working in the next 2 days. Okay, so you can make a note of how the device behaves, okay, and how it can be simulated. So we will prepare notes for tomorrow. Okay. Okay, so we saw about pressure sensor, pressure sensor device, piezo-resistive type is what we will see tomorrow. So I've talked about pressure sensor, so you can, I'll just repeat it like this. Okay, it is connected. Okay, it's connected like this. Okay, so what we see that the displacement, what we see is the force or the elongation that is experienced here is called transverse stress, and the force that is experienced is called longitudinal stress. Transverse, VERSE, transverse stress. So due to which we have a voltage that is changing. So what we do is, how we will do this equation, I'll tell you. Basically, we will apply some 5 volts of voltage. Okay. And then we apply zero pressure. We will simulate it. We will see the voltage drop, V out. Okay. Same 5 volts is kept. 1 Pascal is applied. If I say V out 2. So V2, V out 2 minus V out 1 divided by pressure change, delta P. So this gives me some millivolts per Pascal. So this is my sensitivity of my device. Okay. So 2 is accelerometer. Sorry? So accelerometers are 2 ways, piezo-resistive type and capacitive type, but conventionally we use capacitive type. Okay. So accelerometer is designed like this. It is a vibrating element, right? So it has to have a vibrating element.
Mass is there. Yes.
Sorry?
Mass is two springs are there.
Yes. So we need to have a mass which are connected like this. I'm just writing a simple structure. People have studied like, what if I keep this in the center, what if I keep it here, what if I bring two here. Many researches are going on. Okay, so let's not talk about it. The fundamental functionality is like this, it is suspended, that's all. Whether it is bent or not, in what size, it is irrespective, immaterial. Okay, so it has something called as proof mass. This is called proof mass, 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 proof mass. Okay, so now it is all fixed in this 4 directions. Okay, so now how does this work? So it has a plate in the bottom. Okay, so if I write the cross-sectional view, it is like this. This is the proof mass, and this is the bottom plate. Again, potential of some 5 volts is applied between them. Due to vibration of this proof mass, my delta C keeps changing. So that's how I measure. But this method of it, and though it is very easy to understand, this method is not conventionally used. It is not highly reliable also. Structurally it is not highly reliable. So what people have done is they have modified this slightly and given Ohm's law. Okay, so either it is suspended like this, or it is suspended in the corners, hanging in all 4 corners. It's left to the design engineer. So now what happens if the vibration is in this direction? Okay, the potential is applied between these two. So the functionality is like this. It's vibrating like this. The overlapping area is increasing due to the vibration. Your capacitance increases. Okay, so everything what you need to see is rate of change of capacitance is what is measured. Remember, it is not just change of capacitance, the rate of change of capacitance is measured. Okay, it's measured. So now this is only in one direction, correct? Only in one direction. So that's why it's called single axis accelerometer. Okay, so now I want to increase the sensitivity of the device. So what we do? We keep Ohms here also. So what is the advantage? When this is vibrating, the overlapping area is increasing. When this fellow is vibrating in this direction, the distance between the two is reducing. Right? So you have another set of C is coming. Your C has increased, your capacitance has increased. Okay? So the sensitivity is much more higher for you. So then it is called dual axis or double axis. Okay? Dual axis or double axis. If we have one plate at the bottom and even that direction it is sensing, it is called triple axis accelerometer. Except that, nothing big. So here a standard 5 volts is applied, and then we will see the resonant frequency. This is how we calculate an A and T. Okay, resonant frequency, and then if we have a resonant frequency like this, either this is our bandwidth of operation. We will never run accelerometer at its resonant frequency. Okay, it is always lesser than that. So this region is what we, so I mean just like our resonant circuits, we used to calculate the bandwidth, right? So that's some 2 dB kind of a thing, root 3 or something, we used to do that. So that's what it is. So now we calculate C is equal to epsilon naught A by D, and then we correlate this expression with our simulation output. Okay, so this is the accelerometer part of it. Third comes is gyro. Not too sure whether we'll be able to simulate it because this is a time consuming simulation. Gyro. FEM, it's definitely not possible, but simple can do it. We'll do some simple based or the lumped modeling based gyroscope examples. FEM based it takes at least 1 week to simulate. Okay? Yeah. Okay, so gyroscope. So what is the difference between an accelerometer and a gyroscope?
So you can access
Angular gyroscope is for angular displacement.
Exactly, angular velocity or angular displacement, right? Gyroscope is for angular displacement. So, but when we compare this with accelerometer and a gyroscope, the behavior is like this. This fellow keeps quiet always. Whenever there is a vibration that comes, he vibrates, gives some signal. But gyroscope is not like that. Gyroscope keeps vibrating always. Keeps vibrating always. Okay? Okay? So it keeps vibrating. So if so if this is the case. So it keeps, I think it will write it better. We have one more plate at the bottom. I'll write it with dotted ones. It keeps vibrating. With respect to top view of it, I'm giving you like this. Okay, and just leave this for a while. It is vibrating like this. Okay, always. Now, this vibration always is called the drive mode. Okay, it's called drive mode. So my accelerometer, my gyroscope is in the drive mode, means it is just vibrating by itself at some particular frequency. Now, the purpose of the gyroscope comes here. When we tilt it, when angle changes, reference point changes, then this fellow which was vibrating very much horizontally started behaving like this.
like a pendulum.
Not exactly a pendulum. Maybe it was exactly horizontal. Maybe it started behaving like this. In different. It's meaning to say that the gap between in z direction is somewhere changing.
Different eigenfrequency.
Not eigenfrequency. Not eigenfrequency. So, no, the purpose itself. I mean to say, the purpose meaning the purpose of gyroscope is that only. In case if there is a different capacitance that is observed. Okay, I'll keep it simple. So in drive mode, the rate of change of capacitance is fixed. Correct? I mean the word rate of change of capacitance is fixed. When it comes in all direction, the vibration happens. The rate of change of capacitance between the Z gap is changing very high. The rate of change of capacitance. Then the gyroscope purpose is that is called sense mode. Okay. So usually we have F1. If I say this is the FD and Fs, FD and FS will be very much closer, or it will be like, it is like this, very much closer. Our frequency of drive mode and frequency of sense mode will be very close. Okay, so that's where the purpose of the gyroscope comes in. Say that our gyroscope is not doing the job of sense mode. It's not a gyroscope, it is just an accelerometer. Okay, so this is the only difference between accelerometer and gyroscope. In accelerometer, it is fixed. Whenever vibration comes, it vibrates, it gives you some output. Here it is always vibrating. Whenever there is a reference axis changed, so then the purpose of gyroscope is applied.
So are they are like integrated sensors, like we can use as an integrated.
Actually speaking, IMU, inertial MEMS unit, contains accelerometer, gyroscope and a magnetometer.
Yeah, there's
Three sensors.
I've tried both in practice.
Yeah, of course you have those boards.
Broadcom and Broadcom. Yeah, कितना में Broadcom? ये भी Broadcom वाले मिलता है, 3 9
इधर यूट्यूब पे है ना, यूट्यूब पे है ना. Actually, there is one video. I don't know if I can get it, but actually it is there. चाय तो नहीं आया. So this video you can see the purpose of gyroscope is very much good in this video. This is the drive mode. It keeps vibrating always. Yes. See the reference axis changed? This is sense mode.
लैंप कहाँ से है? सेंटर पे है? हैं?
वो कौन सा है?
उसका जो है वो सेंटर ऑफ ग्रेविटी कहाँ है? सेंटर
नहीं, ये जस्ट कैंटिलीवर बीम जैसा है, वो कोम्स को फिक्स करके रखा है.
वो तो कोम्स को जो अंदर सर्कुलर वाला है,
मिडिल पिन है ना?
हाँ
मिडिल पिन से होगा ना?
हाँ मिडिल पिन जरूर. हाँ yes. This is the graphical representation. What we see next is
comb
drive here.
सर्कुलर कोम ड्राइव टाइप.
Yes, it's called angular gyroscope.
Angular.
Rotatory gyroscope. Right. Okay. So this is the original image of Bosch. Original SEN.
Okay.
So whatever we use the Bosch gyroscopes are this one. Since it's public, of course they have put everything on YouTube.
कुछ जगह पे जो पार्किंग होता है वो ऐसे ही इंक्लाइन व्हीकल को करता है, तो ये सेंसर वो के तो एयरबैग ऑटोमेटिक खुल जाएगा.
नहीं ऐसा नहीं. The rate of change of
अगर पार्किंग होगा तो दोनों रास्ते धीरे से होंगे, लेकिन तो काम तेजी से होगा ना.
So in parking, no, see, during such incidents where you saw, say you are driving at 100 kilometers per hour, suddenly you are coming at 60.
Rate of change.
Rate of change, that's what I am saying, rate of change. It is not just.
होपफुली जो ज़्यादा एक्सेस में चेंज ही बहुत मैक्सिमम हो जाएगा उस टाइम में सब कार्ट रेट हो जाएगा
हाँ. Okay, so that's the purpose. So these three devices, and if time permits, we'll look at bolometer as one example.
During collision तो accelerometer काम करेगा ना? During collision.
इन गायरोस्कोप
No, ठीक है, मगर जब before collision also, if the rate of change of capacitance is sensed beyond the value, it pops up.
Yes. तो gyro और accelerometer दोनों ही काम करेंगे ना?
दोनों काम करेगा.
और during collision तो accelerometer नहीं काम करेगा.
हाँ. नहीं, during collision. नहीं, before collision also, your airbag is already popped up.
How?
Of course.
When the velocity, नहीं ब्रेक भी नहीं लगाई मानना मैंने. When the velocity comes from 100 to 40 within some microseconds, then only the
airbag will pop up. Correct. That's right.
पर collision पहले होगा उसके बाद में तो
airbag. हाँ, correct. हाँ, correct. That's right.
First collision में भी
First collision. Yes. Okay, so these are for automobile applications. Of course, since automobile is very big market, so these are some successful devices which are already implemented. But there are few custom-made sensors and actuators, which based on the requirement of the user, we design it.
MEMS actuators के examples क्या होते हैं?
Cantilever beam is the best example. A cantilever beam can work as many types of sensors.
Inkjet printer is the best example of MEMS actuator.
अच्छा हाँ inkjet displacement
And it also works as biosensor. Okay. So when you mention what you were mentioning of some agricultural thing.
Yeah.
So
I think the Bosch sensor I was talking about, the BME 680. It's a Bosch based sensor.
okay, I don't know the part number. Maybe you have
CS close. It was released in CS 2017. So probably it's still on progress.
Okay.
Sensors are related to the
I mean like three sensors: the environmental sensor, pressure, humidity, and temperature.
Yeah. So one more thing is the capillary pressure. There's one more pressure sensor, meaning capillary pressure is also one more. So that is being developed, and also NO2 sensor.
Is there any options to me like there is a sensor I was reading about the eye temperature sensor? So can we implement it through that?
Whether the temperature range can be done using bolometer, we can check, because bolometer IR captures these temperature things using IR only. Bolometer. We'll talk about bolometer. It's a very simple device, but it can be used as a thermal imaging. Okay. So the is there, it's fine, or else I think what should we do? We'll wind up. So,
Today is a Monday.
yeah, it's a long one.
Yes, sir.
Tomorrow also it will be much longer because it will start at 9, ends at 5.
Today is the first day.
First day.
That's why it's okay.
So, chai vai hai?
So we can import the geometry from other software also. We have to design it.
Some standard you can import, because see, all mechanical softwares have some standard formats you can bring in.
It's just like the AutoCAD design.
Yeah, see, IDES. Yeah, IGES. IGES is a standard format for 3D for any software. You can bring in access files in it.
Can we import?
ANSYS file मतलब you export it as IGES in ANSYS.
और इसको यहाँ import.
your work, this file will not directly import. Your design modular file will not import.
खाली लगे बहुत सारा कोड भी स्पेशियस है सबके पास है सबसे मेन इसलिए स्मार्ट सिटी में सबसे पहले आते हैं सेंटर में